let's start small. We have f0 of n, or f naught of n, equals n plus 1. That's a formula that we can use, and it actually works out very well. So f0 of 3 would be 3 plus 1, which is 4. Okay. f1 of n is f naught of f naught of f naught of f naught, continuing on, of n. So since there's n copies of f naught, really what we're doing is adding 1 n times. So we have n plus 1 plus 1 plus 1, etc. So we end up having n plus n, or 2n. So we can take f1 of n and reduce it to the formula 2n. This will really come in handy as we continue on and do some examples so we can reduce more quickly. f2 of n is very similar. We subtract 1 from the index, so we have f1 of f1 of f1, etc. of n. So we are applying f1 of n, which is 2n. So we'll have 2 times 2 times 2 times 2, and so on until we get to n. So we'll have n2's multiplied together. That's the exponent, 2 to the n power. And we multiply that times the n that existed at the beginning. Okay. So f0, f1, and f2 all have really nice formulas. I know I have f3 written in this box, but the formula does not work very well for f3. And let's take a look at why. Okay, f3 of 1 is f2 of 1, which is 2 times 1, which is 2. Okay, and we get that using the f2 formula. Okay, next we have f3 of 2. So this time there's going to be 2. f2 is written out with a 2 in the center. Okay, so we start on the innermost parentheses. We have f2 of 2. Okay, following our formula, we have 2 times 2 squared, which reduces to 8. And then f2 of 8 is 8 times 2 to the 8th, which is 2048. Again, not such a large number, but it looks to be increasing a little faster than up arrow notation with just those 2's at the beginning. Okay, f3 of 3, so we're increasing n to 3, means we're going to get 3 f2's, and of course the number 3 is going to be larger. So innermost f2 of 3 is going to be 3 times 2 to the 3rd, which ends up being 24. Okay, so next iteration, we've got 24 times 2 to the 24th, which is 402 million. A little bit larger. And then we apply the f2 function again, and we get 402 million times 2 to the 402 million power. So that increased pretty rapidly. Or it was a fast-growing example. All right, let's increase n one more time and take a look at what that does. Because, 2 to the 402 million power is very large, but we're going to see something that's quite a bit larger. Okay, so we're going to have 4 iterations of the f2 function. Start out with 4 times 2 to the 4th, which is 64. 64 times 2 to the 64th. We actually want to rewrite that instead of trying to work it out, because 2 to the 64th power is a really large number, and we're supposed to treat that as a portion of kind of our n, right, in this iteration of the function. So we've got 64 times 2 to the 64th. Well, with, high school algebra skills, we can take the 64 on the left, and we can change that to an equivalent form. 64 is the same thing as 2 to the 6th power. And now that our exponents, those powers, have the same bases, we can add the exponents together. So inside that 2 to the 6th times 2 to the 64, we get 2 to the 70th power. Well, we still have some f2's to work out, so here we go. f2 of 2 to the 70th is 2 to the 70th times 2 to the 2 to the 70th. And this is where things start to get pretty ridiculous. If we try just adding 70 plus 2 to the 70th, because we have that same base going on, that doesn't work out very nicely because 70 plus 2 to the 70th is not an easily worked out number. But we do know that inside those parentheses, 2 to the 70th times 2 to the 2 to the 70th, that's going to be greater than just 2 to the 2 to the 70th power. As we're really just getting rid of the 2 to the 70 that was at the beginning. Okay. Well, if we take f2 of 2 to the 2 to the 70th power, we get something that is bigger than 2 to the 2 to the 2 to the 70th, following the same pattern as before, which of course is bigger than 2 to the 2 to the 16th power. Now, it's quite a bit larger than 2 to the 2 to the 2 to the 16th power, but we're trying to write our exponents with powers of 2, and we're trying to get n at the end, so at the very top of our power tower. So 16 is 2 to the 4th power, so we end up with 4 2s and a 4 in our power tower. So we know that f3 of 4 is greater than 2 to the 2 to the 2 to the 2 to the 4th power, or n 2s and then an n at the very top. Okay. So if we go back to our formulaic options, F0, F1, and F2 were very simple, but F3 does not have a very simple formula, so we end up just kind of saying that it's greater than n 2s in a power tower with the power of n. So the challenge of Magic the Gathering continues. And we started a little while ago talking about a Magic the Gathering deck from 2015 that deals 2 with 408 up arrows of 20 damage. And we know by comparison that Fm of n is between 2 to the m-1 arrows of n plus 1 and 2 to the m-1 arrows of 2n. So really that's about F 409 of 17 damage. So that's quite a few iterations past that F3. So we will not be calculating that out today. The second point here is that more recently, a deck has been created by a player online that goes by the screen name Deedlit, and he's still working on a deck. That deck includes some cards such as Omniscience, which means that basically you don't have to pay for any of the cards that you play, so any of that mana, you don't need any resources for it. And Mimic That, which mimics other cards. So when cards start creating recursion and start comboing to like multiply themselves, and I don't know, it creates just this large ball of damage that gets thrown at the other player. Deedlit was able to do F with an index of omega cubed plus omega times 13 plus 3 of, I'm not even going to read that. We have so many up arrows and 3s, and if you notice, that's all in parentheses. That's the n. So we have some infinite ordinals for our index, and then a number with a ton of up arrows for n. And that's just going to be so ridiculously large. He's actually still working on it. About 2 months ago was his last post. But he and some other Magic the Gathering players have been working on it online. Let's compare that to some other numbers. We have Graham's number, which is actually less than F omega plus 1 of 64. Let's take a look at the index. Omega plus 1 is less than omega cubed, so we already have a smaller index for Graham's number, and our n for Diedlitz's deck is much larger than 64, so we can conclude that Diedlitz's deck can actually deal more than Graham's number worth of damage to the other player, which is really amazing, since in a normal deck, maybe on turn 1 you could deal 3 damage. So he's done quite a bit of work to get this all together. Something that I have run into in my research on this challenge is that there are people who don't know anything about Magic the Gathering, but know about large numbers, so they stumble upon Magic the Gathering and then learn how to play. Or there are players who know nothing about large numbers, they're not math nerds, and they just know a lot about Magic, and then they read these forums, and then they get interested in the math. So it's quite an interesting community that this challenge has created. Even my science major friend that I talked about back at the beginning of this presentation started researching and then talking to some of her patients about really large numbers. Again, I think they were probably just being polite, asking her how her day was going, but she got really excited about learning about Graham's number based on the challenge. So I'm curious what's going to happen if Diedlit and some of the other players will be able to create even more damage in the deck. Or maybe you'll learn Magic the Gathering too and can create a deck of your own. So I've got some resources here. They are clickable links so that you can actually find these websites. The most useful websites that I have found on here are Josh Kerr's Mind Blown, the Fast Growing Hierarchy. It is written in more common language. How to Deal Way Too Much Damage in Magic the Gathering describes Diedlitz's deck, how it is currently, and how you get so much recursion. And then, of course, just Diedlitz's deck is the forum where a lot of people are working on that. The top two and the bottom resources talk a lot about large numbers, and they have been very useful resources in learning all about Googology. Thank you for watching my presentation, and I hope you have a great day.